Hello and welcome back to another video. So to start this video, I am going to explain the driving force for evaporation and explain the diffusion of water and nitrogen. So for this example, we have a pool. So there's going to be liquid water in it. And it says with stagnant vapor phase where a stream of dry nitrogen flows. So this is going to have a screen on top with nitrogen flowing over top. And then the screen here is just so we don't have to worry about convection currents. So we want to look at the diffusion of water and nitrogen. So for diffusion, we want to look at Fick's law. So Fick's law is going to be the molar flux is equal to negative diffusion coefficient times the overall concentration, and this is going to be times the concentration gradient. So this is going to be the driving force. It's the change in concentration of component 1 over the change in area. This can be Z. So here at this water vapor interface, this is where Z is equal to 0. And then here at this interface is where Z is equal to some length. And in this space, this is going to be some mixture of nitrogen and water. And then if we're looking at C, this overall concentration, this is going to be in the units of moles per meters cubed, which is N over V. And if we remember for ideal gas laws, that's PV equals nRT. So this N over V is going to be equal to the pressure over R times temperature. So to put this all together, we have the concentration of nitrogen plus the concentration of water is going to be equal to the total concentration, because those are the only two components that we're looking at in this example. And then we just found that concentration is equal to P over RT. So this is just P over RT of nitrogen plus P over RT of the water is going to be equal to the total concentration. Now let's look at what a concentration gradient will look like for this example. There we go. So for the gradient, I'm just taking this here and just turning it on its side. So on this end, it's going to be, this is going to be from 0 to L. And then this is water, and this is going to be the nitrogen on this side. So right here at Z is equal to 0, this is at the water and vapor interface. So this is where water is going to be at the highest concentration. So let's put that about here. And then as the water diffuses, it's going to get have a lower and lower concentration until it's fully evaporated. So until that happens, the concentration gradient is going to be decreasing along or I guess as you get higher up away from the interface. And then, well, that was for the water, but then in the same respect, same idea, similar for the nitrogen. So that's going to, I'll redraw this a little bit lower. Oops. So you said that water was decreasing as you get further away from the interface. The opposite is true, or it's in the opposite direction rather, for nitrogen, where at the interface, nitrogen is at its lowest concentration, and it gets more concentrated the closer you're getting to the pure nitrogen at the outside of the screen. So as the water is diffusing up, nitrogen is diffusing in the opposite direction, diffusing down. But it does run into the water at some point, and it can't diffuse past that. So we have to look at flux in this case as well. So still using Fick's law, we're going to do the overall flux of component 1 is equal to the molar flux of component 1 plus the mole fraction of component 1 times the overall flux. So this is going to be the total flux is equal to the flux of component 1 plus the flux of component 2. And then for this, N2 is going to be equal to 0. So if we look back at the picture here, we said that the water is diffusing upwards in the positive direction, but the nitrogen, it has nowhere to go. So because it has nowhere to go, like it can't go into the water, the molar flux of nitrogen is going to just be equal to 0. And I'll also put, I'll change the 1s to H2O to make it hopefully easier. And then N2 was the molar flux of nitrogen. Okay. And then now we can write out the overall flux for nitrogen, which is going to be the molar flux of nitrogen plus the mole fraction. This is all in the vapor, or as a vapor rather. So this can be Y instead, because X is used to describe liquids, Y is used to describe vapors. This will be mole fraction of nitrogen times the overall flux, which we just said here. Okay. There we go. We just said that the flux of nitrogen is equal to 0. So this will give us that the molar flux of nitrogen is equal to negative mole fraction of nitrogen times the flux of the water. So now that we have these equations, let's look at an example to piece all of this together. Okay, so here's the values that were given. It's the same example as before, and I just copied down the equations that we just solved for. But for this, we want to estimate the molar flux of water. So we want to solve for that variable. And then for the temperatures in 50 degrees Celsius, it's going to be 323 Kelvin. So now if we want to solve for the concentration, we would need to use, well, we have to find the pressure. And to find the pressure, we need to use either the Antoine equation or the Clausius-Clapeyron equation. So for Antoine, it's going to be the log of the saturated pressure going to be equal to, these are all normally in the table. It's going to be A minus B over C plus the temperature. And then for the other equation, it's going to be the natural log of the saturated pressure 2 over pressure 1 is going to be equal to the negative change in molar enthalpy of vaporization over the ideal gas constant times 1 over the temperature of component 2 minus 1 over T1. Okay, so if I'm trying to find the concentration of water, it's going to be equal to the saturated pressure, which I'm not going to calculate, but it's going to be 12 times 10 to the third pascals. It's going to be over the, oh, well, this is going to be the saturated pressure of water, specifically at 323 Kelvin that we were given before. Okay, and then now that let's erase this. Now that we know the pressure or the saturated pressure of the water, we can find the saturated pressure of the nitrogen. Because the pressure of nitrogen plus the pressure of the water is going to be equal to 1 bar up here. So this will be 12 times 10 to the third pascals, and then 1 bar is equal to 10 to the fifth pascals. And so if we subtract this, it's going to be equal to 88 times 10 to the third. Okay, so I'm going to erase this, get this out of the way. So now we know pressure of the water, we said, is 12 times 10 to the third pascals. And pressure of the nitrogen is equal to 88 times 10 to the third pascals. Just to clean this up a bit, so erase all this as well. Okay, so that part's done. We also want to find the mole fraction of the water. So to do that, we have mole fraction of water. We can put this equal to the partial pressure of water over the total pressure. So that's going to be 12 times 10 to the third over 10 to the fifth. And this will be equal to 0.12. This is happening at the interface. Z is equal to 0. So that's right there. Okay. And then the mole fraction of water at Z is equal to 1. This will be up here. This is at 1 meter. That's given to us. That the length is 1. The mole fraction of water is going to be equal to 0 because that's at the top. So now let's look at an equation. So we're trying to find the molar flux of the water. So that's going to be equal to the flux of the water that's up here. This is going to be negative diffusion coefficient times the concentration times the change in mole fraction of water over change in position, and then this part will be plus mole fraction of water times the total flux, which we said since the flux of nitrogen is equal to 0, it should be into. We can just say this is the molar flux of, or the total flux of water. And then let me move all of this over real quick because the concentration is going to be pressure over ideal gas constant times temperature. So now I can subtract this term over. I'm going to have flux of the water minus mole fraction of water times the flux of water. Still going to be equal to negative diffusion coefficient times pressure over ideal gas constant times temperature times the change in mole fraction of water over change in position. And then on the left side, we can factor out the flux of the water. So if we factor this out, it's going to be multiplied by 1 minus mole fraction of water. And then the right side stays the same. So I'm just going to copy this down. So now we will divide by this term and then multiply the dz over. That way we can integrate. So we have the flux of the water dz is equal to negative diffusion coefficient. I'll just put this together. Times pressure over the ideal gas constant times temperature times change in mole fraction of water over 1 minus mole fraction of water. I'll actually just put this like that. There we go. That's fine. So to integrate, it'll be here and here. I'll just rewrite it though. So the change in position is going to go from 0 to 1 meters. It's going to be equal to the negative diffusion coefficient times pressure over RT. Excuse me. We're going to integrate this from we said at the interface that the mole fraction was 0.12, and then at the surface it was 0, and again this will all stay the same. There we go. So when we integrate this first term is going to be 1. So we're going to be left with the flux of the water is equal to dP over RT times the natural log of mole fraction of water minus 1. This is going to be from 0.120. So we're going to be left with this equation. 1 over, this is going to be 88. Alright. If we plug in the values from before, it's going to move this up here. Okay. Then we have the flux of the water is equal to, we said that the diffusion coefficient is 10 to the negative 5 meters squared per second. The pressure we said was 10 to the 5th pascals. The ideal gas constant is 8.314 joules per mole Kelvin. Temperature we said was 323 Kelvin. And then we have the natural log of 1 over 88. Alright. And then we have some issues with our units. So first, we need to fix the pascals. We have pascals is equal to Newton per meter squared. Newtons are in kilograms, meters per second squared. And then we still have the meter squared at the bottom and the denominator. So then we can change the pascals to be, to be in kilograms per second squared times meters. We also have an issue with the joules. So joules is going to be a Newton meter, which is going to be kilograms times meters squared per second squared. So let's rewrite this down here. 10 to the negative 5th is still in meters squared per second times 10 to the 5th kilogram per second squared times meters over joules is 8.314 kilograms meter squared over second squared moles Kelvin. It's going to be times 323 Kelvin times natural log of 1 over 88. Okay, and then I wrote this one wrong, so let me change that. Okay, now we can cancel out some units. So we have Kelvins cancel, meters squared, this will just be meters. Kilograms cancel, second squared cancels. Now we can finally calculate this. And I got that it was 4.76 times 10 to the negative 5th. And this is going to be in moles per meter squared times seconds. And that's going to be the flux of the water.